Okay, so enthalpy of formation. So imagine you just take a collection of elements and use it to build the compounds you're looking at. That is your formation reaction. Okay. So, combine hydrogen and oxygen, you make water. That is the formation of water. If you combine hydrogen and oxygen, you make water. And that's the formation of water. Yes, that I pretty much repeated myself. But in this case, you're making liquid water. In this case, you're making gaseous water. Remember, the state of matter matters. The state of matter is important. Liquid versus gas. So when you make liquid water, the enthalpy of formation, is negative 285.8. For gaseous water, it's negative 241.8. Okay. It takes about 44 kilojoules per mole to boil water, remember? And here we combine carbon, oxygen, and hydrogen to get sugar with an enthalpy of formation of 1273. So that's what an enthalpy of formation is. It's really simple. You have your elements on the left, you have your compound on the right. The slight complication is that you always produce 1 mole of your product. Okay, so 1 mole of water, 1 mole of water, 1 mole of sugar. Which means enthalpy of formation breaks the fraction rule. Okay, you can have fractional coefficients. Okay, because an enthalpy of formation always produces 1 mole of your product, no matter what. Over here on the right, we have a typical table. Okay, I just Googled it, so it's table 5.3 in some book. Standard enthalpies of formation at 298 Kelvin. So notice it's standard, and it tells you the temperature that we're talking about, 25 degrees Celsius. So here we have the symbol, enthalpy of formation, delta H sub F for formation, and then it's got the standard little dot. Okay. So this is just a whole bunch of compounds, standard enthalpies of formation for those compounds. Okay. So acetylene, C2H2, enthalpy of formation is positive 226.7. You have to put a lot of energy in order to make. I'm pretty sure that is a mistake on this slide. This should almost certainly be positive 1273 to make sugar. Do we have sugar anywhere on this chart? We do. Glucose. No, it's negative 1273. Huh. I am kind of surprised. Okay, I shouldn't be too surprised. We're combining carbon and oxygen. All right, anyway. So enthalpy of formation. You produce 1 mole of your product. Be careful. Pay attention to the state of matter of your thing. And it's just made out of pure elements. So what this means is that by definition, because of the way we have this set up, a pure element, the enthalpy of formation is always going to be 0. Because you're just making hydrogen into hydrogen. That's same thing to same thing. Enthalpy of formation for a pure element in its standard state is going to be 0. So hydrogen gas at 25 degrees Celsius is going to have an enthalpy formation of 0. Liquid hydrogen at 25 degrees Celsius is not going to be 0 because that's not its standard state. Okay, so why do we do this? Because the appropriate reactions for a Hess's law problem aren't always present. Okay, sometimes you have to, you can't always, just find the. You can't always find the random collection of reactions that you need to get from A to Z. Okay? But the elements are always there. So you are trying to find the enthalpy of reaction for something going from reactants to products. Well, you just break it down into your elements, and then you put those elements back together into their products. How does this work? For example, sugar plus oxygen makes CO2 and H2O. We pretend that we break all of our reactants down into their elements. So, for example, sugar broken down into carbon, hydrogen, and oxygen. Oxygen is already an element. Okay, so these first 2 reactions, we're breaking our reactants down into elements. And then we put those elements back together to make our products, our carbon dioxide and our water. So sugar, or carbon plus oxygen makes carbon dioxide, hydrogen plus oxygen makes water. And look, sugar broken down into its elements, that's just the reverse of the enthalpy of formation. So the enthalpy of reaction for this is negative enthalpy of formation of sugar. Oxygen's an element, whatever, enthalpy of formation is 0. We combine carbon and oxygen to make our 6 carbon dioxides, and the enthalpy of that reaction is 6 times the enthalpy of formation. We combine hydrogen and oxygen to make 6 waters. That's just 6 times the enthalpy of formation of water. And then we add all of those reactions together. Enthalpy of reaction 1 plus enthalpy 2 plus enthalpy 3. So negative the enthalpy of formation of sugar plus 6 times the enthalpy of formation of water plus 6 times the enthalpy of formation of CO2, because that's just exactly what we have here. 6 times CO2, 6 times water, negative sugar. We rearrange that slightly. We have sugar, water and carbon dioxide, 6 plus 6, and then we subtract the enthalpy of formation of sugar. It is not an accident that that is our products minus our reactants. 6 carbon dioxide, 6 water as our products, 1 sugar as our reactants, and then an elemental oxygen, which, whatever. So products minus reactants. This is going to happen a lot. Okay? Products minus reactants is very, very common. It's something that you see all the time. Okay? Products minus reactants. Remember that. Products minus reactants. So, generally, for any reaction, so long as you can find the enthalpy of formation for every product and reactant, the standard enthalpy of formation for every product and reactant, then the enthalpy of reaction is going to be products multiplied by their coefficients added together. You take your reactants, multiply them by their coefficients, then add them together. Then products minus reactants. That is a complicated way of writing it out, but just remember, you take all those enthalpies of formation, you multiply everything by their coefficients, add the products together, add the reactants together, products minus reactants. So, calcium carbonate, calcium oxide, CO2. So what is the enthalpy of reaction for calcium carbonate breaking down into calcium oxide and carbon dioxide? Well, we have our numbers right over here. Here's calcium carbonate, here's calcium oxide, and here's carbon dioxide. All right in a row. So let's go ahead and write it out. Ooh. Crap, is going to try saving, isn't it? All right. So, calcium carbonate goes to calcium oxide plus carbon dioxide. Ooh. Gotta be careful with that lag. CO2. All right. So we just grabbed the enthalpies of formation off that table. So for calcium carbonate, it's negative 1207.1. For calcium oxide, it's negative 635.5. For carbon dioxide, it's negative 393.5. And then we add our reactants together, we add our products together. So our reactants add up to negative 1207.07.1. Our products add up to 0.9201 negative. And then it's going to be products minus reactants. So it's going to be negative 1029.0 minus negative 1207.1. There's going to be lots of negative signs flying around for these things. A lot of enthalpy of formation are negative, and then products minus reactants. So it can be a problem. You're just going to have to get used to that and try not to make mistakes. Keep track of your negative signs, as always. And you do that, it's going to be 1, 8, 7, 1. So positive 178.1, and all those numbers were kilojoules. Okay. So you have to put in 178.1 kilojoules of energy for every mole of calcium carbonate you want to decompose. Rather simple. Now let's look at the next one. Two sugar molecules combining to make sucrose and water. Okay. This is just a dehydration synthesis for those of you who have studied some biology. So, once again, our enthalpy of reaction is products minus reactants. So, our products, we have one sucrose molecule. Looking at that table, that is going to be negative 2221. And one water, but be careful. Okay, because this is liquid water. Okay. And over here we have both liquid and gaseous water. You want to make sure you get the right form. Okay. So liquid water is negative 285.8. And then we subtract our reactants. And this is where our coefficients come into play, because you take a look, there are two sugar molecules going into this. Okay. So 2 times negative 1273. Okay. Don't forget your coefficients. And as always, be careful of those negative signs. I'm going to never stop harping on that, because they will screw you up quite a lot. So 1273 times 2 minus 285.8 minus 2221. And our answer is positive 39.2 kilojoules per mole. It takes a little bit of energy to build those complex sugars. Not a heck of a lot, but a little. All right, so now let's go ahead and look at the third one. Methane combining to make propane and releasing a little bit of hydrogen. Okay. So we have 3 methane makes 1 propane and 2 hydrogen. And those, well, here we have methane, 74.8, propane right below it, 103.85, but hydrogen isn't on here. Hydrogen is an element in its native state, therefore the enthalpy of formation is 0. Okay, keep an eye out for those elements. Enthalpy of formation for an element in its native state is 0. So once again, enthalpy of reaction is products minus reactants. So propane is negative 103.85 plus 2 times 0. Ooh, that's 0 because hydrogen is an element in its native state. Then we subtract our reactants. There are 3 methanes, and methane is negative 74.8. I'm not going to try and do this one in my head. Then minus 103.85. The answer is 120.6. Okay. To combine a couple of methanes to make propane, you have to put in 120.6 kilojoules of energy. It is an endothermic reaction. All right. So enthalpy of formation problems are quite a bit simpler than your other Hess's law problems. Okay. Because you're just putting together a few simple numbers. You just look up the numbers on a table. You cannot memorize these numbers. There is a different enthalpy of formation for every single substance out there. If they give you an enthalpy of formation problem on the test, they will have to give you or they might. Well, because, this test this semester is going to be at home, they might expect you to use the textbook, okay? You have to use a table to look these numbers up. That's what I'm trying to tell you. Okay. So here's some more examples. I think these problems are fairly simple, fairly straightforward. You should have already seen them in lab, so I'm going to go ahead and skip over this. Okay. Here's another example of a table. This is to be used with these problems right here. Right. These tables are huge. Remember the gigantic book at the front of lab? A big chunk of that book is taken up by tables and tables and tables, pages and pages and pages of numbers like these. It's just unavoidable. That is really what those books were for once upon a time. Now we have the internet. All right, so now let's move on from enthalpy of formation to bond enthalpy. Bond enthalpy is very similar to enthalpy of formation, except that it uses bonds. Okay. This is what you use if you don't have an enthalpy of formation. Okay, you use the bond energy. Okay, you say, okay, what happens? Okay, remember enthalpy of formation. You say, what if you pulled the reactants apart into their elements and then put those elements back together as their products? You do pretty much the same thing. Only instead of pulling it apart into its elements, you're actually breaking every single bond in the reactants and then putting those back together as products. Okay. Remember, bonds tie atoms together, so you have to put energy in order to break those bonds, in order to pull the to pull the elements apart. No, you don't get to play with. That's my pen, Sasha. All right. So this is a much simpler number. It's a much smaller table. So this is a set of bond enthalpies. Okay? This is how much energy is needed to break those bonds. Okay? So here we have a carbon-hydrogen bond. It takes 413 kilojoules of energy to break a carbon-hydrogen bond. Carbon-carbon bond is 348. Carbon-nitrogen is 293. Carbon-oxygen is 358. But a carbon-oxygen double bond is 799. Okay? More bonds is stronger. So be careful. Make sure you're looking at the correct kind of bond. Okay? A single bond is not the same thing as a double bond, is not the same thing as a triple bond. Okay? So make it a point to make sure you're looking at the correct kind of bond. Now, the other thing about these numbers is that they are only okay. Okay? These are rough numbers because every bond is shaped by its environment. Okay? First up, methane. Okay? if you take the methane molecule, it has 4 carbon-hydrogen bonds. Each of those bonds is perfectly identical. But when you pull apart methane, you pull off the first hydrogen, and that takes a certain amount of energy, energy 1. You pull off a second hydrogen, that takes a different amount of energy, energy 2. You pull off a third one, that takes, a third energy. You pull off the final hydrogen, then that is the fourth energy. And then they say that the carbon-hydrogen bond is the average of those 4 numbers. And that's not really true, but it's not true. It's weird because this final bond, you've pulled off 3 hydrogens. You've made a very, very different environment. This carbon-hydrogen monstrosity right here it's a very different sort of thing from this guy up here. So it's kind of weird. And on top of that, this is how you measure carbon-hydrogen bond, but it's how you measure the carbon-hydrogen bonds in methane. The carbon-hydrogen bonds in other molecules are going to be different. There's just no way about it. These numbers are rough. They are not the most accurate thing in the world. So, the way we use bond enthalpies is the reverse of Hess. I know. Don't expect consistency. It's bad. So, the enthalpy of reaction using bond enthalpies is you add up all of the bonds in your reactants, you add up all the bonds in your products, and then it's reactants minus products. So it's the reverse of what we've been doing. Hess's law was products minus reactants. Bond enthalpy is reactants minus products. So, for example, propane. Propane plus oxygen makes CO2 and H2O. Okay. So we have 5 oxygen-oxygen double bonds in our reactants. Each of those is 495. Okay, these numbers are right off of this table right here. So oxygen-oxygen double bond, 495 kilojoules per mole. And then we have 2 carbon-carbon single bonds. Okay, that's here inside of propane. Each one of those is 348 kilojoules per mole. And then we have 8 carbon-hydrogen single bonds, so 413 kilojoules per mole. Okay. So 495 times 5, 348 times 2, 413 times 8. You add those numbers together. On the reactant side, we have 6475 kilojoules. Coming over to the products, we have 6 carbon-oxygen double bonds. Be careful about that. That is something that you will make a mistake with. I know because I made this mistake when I was making this slide. Okay, we have 3 carbon dioxide molecules. Each of those molecules has 2 carbon-oxygen double bonds. Remember, carbon bound to oxygen on one side, bound to oxygen on the other side. Okay, so 6 carbon-oxygen double bonds. And then likewise for water, 4 water molecules means 8 oxygen-hydrogen single bonds. So 799 times 6, 463 times 8, you add them together, 8498. Reactants times products, or reactants minus products, 6475 minus 8498 is 2023 kilojoules, negative 2023 kilojoules per mole. The actual enthalpy of reaction for propane is negative 2219.2 kilojoules per mole. So it's not the worst thing in the world, negative 2,000 versus negative 2,200. But the fact is, that's about 200 kilojoules per mole. 200 kilojoules per mole is 5 times what it takes to boil water. Okay, this is not insignificant. Okay, that's a 10% difference. 10%, that's going to cost you points on anything. That's a whole letter grade, right? I mean, that is a pretty big difference. These are rough numbers. Okay, they would not be enough to this is not something you're going to do for precision work. It's a rough guide. All right, so here's an example. Hexane plus oxygen makes CO2 and H2O. Just real quick, let's go ahead and hop on over to Paint so I can show you what hexane looks like. 2, 3, 4, 5, 6, 9, 10, 11, 12, 13, 14, 1, 2, 3, 4, 5. All right, so that is what hexane looks like. It's going to have 5 carbon-carbon bonds. I say 5 because there's only 5. 1, 2, 3, 4, 5. Okay. Easy mistake to make. And then there are going to be 14 carbon-hydrogen single bonds. Okay. So that is for you, an exercise for you to do this problem yourself. It's not particularly difficult, but it'll take you a little bit of time. Okay. So bond enthalpies are annoying. They are not the most precise things in the world, but they're useful. They're a rough and ready guide. Okay, they won't get you, the really precise things so that you'll be able to calculate how much energy it'll take, so that you can do, an actual like an industrial thing or a lab thing or anything like that. But it'll give you a rough idea, so that you'll know about how much energy it'll take, so that you can start doing your prep work and your setup if you had to do something in a lab or something like that. All right. And with that, we are done with this set of slides. That means we're done with today's lectures. So I will once again pause for questions, and then I will see you on the morrow.